Hey everyone, I hope you're doing well today. In this video, I'm going to cover 5 different practice problems where we verified trigonometric identities. Pause to check out the timestamps and feel free to jump around the video by using them in the description. While I know there are more identities out there, this video is going to be focused on using these ratio identities and these Pythagorean identities. I recommend that you either pause the video to try to memorize these identities, or take a screenshot to use as a reference as you work on the problems. If you want, you can pause at the beginning of each practice problem and try them on your own before I go over them, or you can just play the video through and we can work on them together. Grab some paper and something to write with, and let's do some math together. Here in example 1, we have secant of theta minus cosine of theta over secant of theta is equal to sine squared of theta. Pause the video now if you'd like to try this on your own first. Otherwise, you can just keep playing the video and we can go over it together. Since the left side is a lot more complicated than the right side, we're going to try to simplify it to make it match the sine squared of theta. Right from the beginning, I don't see any obvious ratio or Pythagorean identities. So instead, I'm going to see if I can rewrite this fraction on the left side here. I'm going to start by splitting this fraction into 2 separate fractions. I'm going to write secant of theta over secant of theta minus cosine of theta over secant of theta. Even though we separate it into 2 separate fractions, this is equivalent to the original fraction. The reason why this is useful is that we can simplify the secant theta over secant theta to just getting 1. Simplifying this, we can write 1 minus cosine of theta over secant of theta. At this point, it's important to notice that cosine and secant are reciprocal functions. What I mean is that cosine is the same thing as 1 over secant, and secant is the same thing as 1 over cosine. To make this more clear, I'm going to separate these 2 functions. I'm going to write this as cosine of theta, or cosine of theta over 1, multiplied by 1 over secant of theta. Cosine theta over 1 is just cosine of theta, and 1 over secant of theta is the same thing as cosine of theta. From this, we can multiply this cosine of theta by cosine of theta, and write cosine squared of theta. This is where you want to remember your Pythagorean identity, where sine squared of theta plus cosine squared of theta is equal to 1. Rearranging this identity, we can say that 1 minus cosine squared of theta is equal to sine squared of theta. That means we can rewrite this 1 minus cosine squared of theta as sine squared of theta. Here we can see that we verified the identity. Besides using the Pythagorean identity, we did use the reciprocal identity of cosine of theta is equal to 1 over secant of theta. These 2 identities helped us verify this problem. Here in example 2, we have 1 minus sine of x over cosine of x is equal to cosine of x over 1 plus sine of x. While sometimes it's hard to decide which side to manipulate to make it look like the other side, I try to see which side looks a little bit more like one of our trig identities. Looking at all of our trig identities here, this numerator of 1 minus sine of x looks kind of close to the sine squared plus cosine squared equal to 1, but manipulated a little bit. Moving around this Pythagorean identity, we can say that cosine squared of theta is equal to 1 minus sine squared of theta. As you practice these trig identities more, you might start to notice that this 1 minus sine of x in the numerator looks really similar to this 1 minus sine squared of theta. Since the left side looks a little bit easier to manipulate, let's verify that the left side of this equation is equal to the right side. Let's take this left side of 1 minus sine of x over cosine of x and multiply it by 1 plus sine of x over 1 plus sine of x. Since this is really just equal to 1, we're not changing the value of this left side. We're multiplying the top and bottom by 1 plus sine of x because we have a difference of squares pattern here. Remember when you have the pattern of something like a minus b multiplied by a plus b, the product of that is just going to be a squared minus b squared. Since 1 minus sine of x multiplied by 1 plus sine of x fits this pattern, we can rewrite the numerator as 1 minus sine squared of x. While you could FOIL the numerator out, I promise you're going to get this difference of squares. In the denominator, we're just going to multiply this cosine of x by 1 plus sine of x, and write cosine of x multiplied by 1 plus sine of x. Hopefully you're excited to see this numerator of 1 minus sine squared of x, because it matches one of our Pythagorean identities, written in a different way. Remember that 1 minus sine squared of x is the same thing as cosine squared of x. Substituting that in, we can write cosine squared of x over cosine of x multiplied by 1 plus sine of x. Since the numerator and denominator have a GCF of cosine of x, we can divide the top and bottom both by cosine of x, and we'll be left with cosine of x over 1 plus sine of x. Here we can see we verified this identity. In example 3, we're going to verify that cosine of x over 1 plus sine of x plus 1 plus sine of x over cosine of x is equal to 2 times secant of x. A little more obvious than the last problem, we're going to simplify this left side to make it look like the right side. Since I don't see any identities I can use right away, I'm going to take these two fractions and try and combine them to write one fraction. In order to do that, we're going to have common denominators first. For this first fraction, we're going to multiply it by cosine of x over cosine of x. And for a second fraction, we're going to multiply it by 1 plus sine of x over 1 plus sine of x. Remember that this is technically equal to 1, and this is also technically equal to 1. Multiplying these fractions together, we're going to get cosine squared of x over 1 plus sine of x multiplied by cosine of x. Multiplying these two fractions together, we're going to get 1 plus sine of x squared over 1 plus sine of x multiplied by cosine of x. Now that we have common denominators, we can combine the two fractions to write it as 1. It's a good idea to pause every once in a while to see if there's any identities that you might be able to use. Unfortunately, I don't see any identities that we can use here. And so, the only thing I can think of doing right now is foiling out this 1 plus sine of x squared. Foiling it out, we're going to have cosine squared of x plus 1 plus 2 sine of x plus sine squared of x. This is still all over the quantity of 1 plus sine of x times cosine of x. Now let's think if we can use any Pythagorean identities since we have a bunch of these squared trig functions. Remember this good old identity of sine squared of theta plus cosine squared of theta is equal to 1. Since we have a cosine squared of x and a sine squared of x added together in the numerator, we can simplify that to just writing 1. Continuing this and combining those together, we're going to get 1 plus 2 sine of x all over this same denominator. This 1 plus 1 is equal to 2, so we can write 2 plus 2 times sine of x. And this is still going to be over the quantity of 1 plus sine of x times cosine of x. In the numerator, let's factor out the GCF and write 2 times the quantity of 1 plus sine of x. And for now, that's still going to be over all of this. At this point, this 1 plus sine of x is the GCF of the numerator and denominator, so we can cancel those out. And we can write 2 over cosine of x. Since we're trying to get secant of x, let's rewrite this as 2 times 1 over cosine of x. And since 1 over cosine of x is the same thing as secant of x, using a reciprocal identity, we can write this as 2 times secant of x. After all that, we finally verified this identity. In example 4, we're going to verify that cosine of x times cotangent of x over 1 minus sine of x minus 1 is equal to cosecant of x. The strategy I'm going to use to verify this trig identity is I'm going to simplify the left side to make it look like the right side. First, I'm going to rewrite the left side as one fraction, so I need common denominators. Multiplying this 1 by 1 minus sine of x over 1 minus sine of x, we can rewrite the 1 as 1 minus sine of x over 1 minus sine of x. Now that we have common denominators, we can rewrite this as one fraction and write cosine of x multiplied by cotangent of x minus the quantity of 1 minus sine of x. This is going to be all over 1 minus sine of x. Distributing this negative here, we can write this as cosine of x times cotangent of x minus 1 plus sine of x. This is still going to be all over 1 minus sine of x. Let's keep working on this up here. The only thing I can think of rewriting right now is this cotangent of x. Remember that one of our trig identities is that cotangent of x is equal to cosine of x over sine of x. Substituting in cosine of x over sine of x for cotangent of x, we can write cosine of x multiplied by cosine of x over sine of x minus 1 plus sine of x. And that's all over 1 minus sine of x. Multiplying these two together, we're going to get cosine squared of x on top of sine of x. In the numerator, we still have this minus 1 plus sine of x. And this is still on top of 1 minus sine of x. At this point, the numerator is still looking pretty messy. My initial thought of trying to get rid of this cosine squared of x is by trying to add some sort of sine squared of x to it to get 1 using the Pythagorean identity. To do that, we're going to have to rewrite the rest of the numerator all over sine of x. So let's get common denominators now. Let's take this 1 and multiply it by sine of x over sine of x. And let's take this sine of x and also multiply it by sine of x over sine of x. From that, we're going to have cosine squared of x over sine of x minus sine of x over sine of x plus sine squared of x, because sine of x times sine of x on top is sine squared of x, over sine of x. This whole thing is still over 1 minus sine of x. Now that the three fractions in the numerator have common denominators of sine of x, we can combine them all into one fraction. We can write cosine squared of x minus sine of x plus sine squared of x over sine of x. This is the numerator, but that's all over 1 minus sine of x. At this point, notice that we have a cosine squared of x plus sine squared of x in the numerator, and that can be combined to make 1 using the Pythagorean identity. So in the numerator of the numerator, we can write 1 minus sine of x, and this is over sine of x. And instead of writing all of this over 1 minus sine of x, or dividing it by 1 minus sine of x, I'm going to multiply it by the reciprocal and multiply it by 1 over 1 minus sine of x. Remember that instead of dividing by something, we can just multiply by its reciprocal. The reason why I'm going to do this is because this 1 minus sine of x can cross cancel with this 1 minus sine of x down here. These are going to just simplify to make 1, and we'll have 1 over sine of x. Hopefully this is a reciprocal trig function that you recognize, and we can rewrite this as cosecant of x. And finally, we verified that the left side does equal cosecant of x. And here's example 5, the last problem in this video. We have sine to the 4th power of x minus cosine to the 4th power of x over sine squared of x minus cosine squared of x is equal to 1. Let's simplify this left side to match the right side. While these trig functions raised to the 4th power are a little intimidating, try not to overthink them too much. Try to remember from Algebra 2 that we have the difference of squares pattern of a squared minus b squared is equal to the quantity of a plus b times the quantity of a minus b. While I know that's a little different than raising it to the 4th power, this pattern still works. If we had something like a to the 4th power minus b to the 4th power, this is still a difference of squares. We could write this as the quantity of a squared plus b squared times the quantity of a squared minus b squared. And since this a squared minus b squared is another difference of squares, it can factor further. We could technically factor one more time and write a squared plus b squared multiplied by the quantity of a plus b times the quantity of a minus b. Let's try to apply that same knowledge to these trig functions. Let's rewrite this sine to the 4th power of x as the quantity of sine squared of x squared. And let's rewrite this cosine to the 4th power of x as cosine squared of x raised to the 2nd power. This is all over the same denominator. Since we have a difference of squares here, we can rewrite this as sine squared of x plus cosine squared of x multiplied by sine squared of x minus cosine squared of x. And underneath, we still have this sine squared of x minus cosine squared of x. Since the denominator actually matches one of the factors of the numerator perfectly, we can cross cancel them. Simplifying this, we just have sine squared of x plus cosine squared of x. Hopefully this looks familiar because we can just use the Pythagorean identity and say this is equal to 1. And there we have it, we verified this trig identity. And that wraps up this video on 5 practice problems on verifying trigonometric identities. If you found this video helpful, please give it a thumbs up and let me know in the comment section below. Keep up the good work, and I'll see you in the next one.